Okay, let's unpack this. The sheer complexity and interconnectedness of a modern aircraft.
It's really something, isn't it?
From the moment it leaves the gate to its final landing, you've got hundreds of intricate systems working in perfect harmony, this symphony of engineering. But what does it really take to keep these marvels of flight flying safely and efficiently, day in and day out?
What's truly fascinating here is that beneath that polished exterior, an aircraft isn't just like a collection of parts. It's a living, breathing network. Every rivet, every wire, every single line of code is designed with layers upon layers of redundancy and precision.
Uh-huh.
Understanding this anatomy isn't just about memorizing names.
Yeah.
It's about grasping the why behind every component, its critical role, and, well, the domino effect if something goes wrong. It's about anticipating challenges, ensuring resilience.
Exactly. And for anyone deeply involved in aviation maintenance, whether you're an engineer student building your foundational knowledge, maybe aiming for that EASA B1.1 or B2 certification.
Right, those key qualifications.
Or maybe you're a seasoned professional looking to refresh your expertise and connect the dots across different disciplines. Well, this deep dive is really custom tailored for you. Today, we're taking a shortcut sort of through the vast essential landscape of aircraft structures and systems, and we're drawing directly from the essential EASA Module 13 training material.
Yeah, our mission here is really to distill the most important nuggets of knowledge, helping you navigate the complexities of aircraft systems. We'll cover everything from, the basic principles that keep a plane in the air,
The real fundamentals.
to the cutting-edge digital avionics that manage its every move. We're going to highlight the practical implications for maintenance and operations, focusing on those aha moments.
The aha moments. Love those.
Yeah, the ones that bridge theory and the actual hangar floor. Get ready to think about these systems in maybe a whole new light.
So what does this all mean for your career, for your daily work, and for your overall understanding of these incredible machines? You're about to get a comprehensive, yet I hope, engaging overview that connects the dots across these critical domains. You'll understand not just what a system does, but why it's built the way it is, and what that means for your role in keeping it safe. Let's dive in.
Let's do it.
The foundations, standards, structures in the air.
Okay, before we even touch a wrench or, a digital diagnostic tool these days,
Right, more likely.
there's this crucial framework that governs absolutely everything. We're talking about the bedrock of aviation safety, EASA certification and global standards. Why is this our starting point?
Precisely. It has to be. The Aviation Maintenance Technician Certification Series material we're drawing from today is geared towards B2 certification, that's for avionics, but it also heavily cross-references B1.1 for airplane turbines. These certifications, like EASA Part 66, they ensure a standardized level of knowledge and experience across different categories. So whether you're an A1 working on small piston aircraft, or a B1.1 on large commercial jets, or maybe a B2 specialist focusing on avionics, it means there's a common baseline you're expected to meet. It ensures consistent competence worldwide. Think of it as the universal language of aviation safety.
So this common baseline isn't just about technical knowledge, but about fostering global collaboration and, well, trust in maintenance teams, right?
Absolutely. Trust is huge.
And it's not just about what you know, but how you communicate it globally.
Yeah.
I remember first encountering the ICAO standard for writing numbers,
Oh, yeah, that catches people out.
using spaces instead of commas, or periods like one space, thousand space, thousands, instead of one comma, thousand down. That might seem like a really small detail, but when you're dealing with critical data like fuel loads or altitudes, ambiguity is just not an option.
That's a crucial distinction. This global standardization, from number notation to the consistent use of SI units, the International System of Units, it's fundamental for precision. In all calculations, all measurements, for every aspect of international civil aviation operations. It just eliminates confusion,
Right?
enhances safety, and allows maintenance professionals from different regions to work seamlessly on the same aircraft. Imagine the chaos.
Oh, I can imagine.
If a technician in one country used pounds and another used kilograms for the same critical component, or if a wiring diagram was misread because of different number formats, it's truly the bedrock of global aviation.
Okay, with that bedrock firmly in place, let's kick off with the very essence of why these machines defy gravity: the theory of flight. Now, this isn't just for pilots. As AMEs, you absolutely need to understand the fundamental forces and how they interact with the aircraft's design, because those interactions directly affect the airframe and the systems you maintain.
Indeed. We're looking at aerodynamic principles, like the different speed regimes. For an AME, the crucial takeaway here is that how air behaves at subsonic versus transonic speeds dramatically impacts structural loads and the center of pressure.
Okay, so it's not just abstract theory.
Not at all. This isn't just pilot knowledge. It means completely different stress points and inspection requirements depending on the aircraft's typical operating envelope. Think of it. Subsonic is below Mach 0.75, where air flows pretty smoothly around the aircraft.
Right.
But then you hit transonic from Mach 0.75 to 1.20. That's where parts of the aircraft, especially over the wings, start experiencing supersonic flow. You get shock waves forming, leading to significant aerodynamic challenges. This is where designing the structure becomes really complex, where seemingly small imperfections can cause big problems. Above that, you have supersonic and then hypersonic above Mach 5.00. Each regime presents unique challenges, forces, heat, material stress that directly impact your maintenance protocols.
And how those incredible forces are managed. We have primary flight control surfaces, ailerons, elevators, rudders controlling roll, pitch, and yaw, respectively. Simple enough on the surface.
Seems simple, yeah.
But then there are also secondary or auxiliary controls that are equally vital for different phases of flight.
Right. Think high-lift devices. You've got trailing edge flaps deploying from the back of the wing. They significantly increase the wing's surface area and curvature, generating more lift, and, importantly, more drag.
Crucial for landing.
Crucial for reducing takeoff and landing speeds, allowing the aircraft to operate safely at slower airspeeds without stalling. Then there are leading-edge slats and leading-edge flaps on the front of the wing. They also extend to improve lift at lower speeds, often creating a slot to smooth airflow over the top of the wing, delaying the stall. Spoilers are another key element, those panels on the upper wing surface that raise up to the airstream.
Speed brakes, basically.
Often used as speed brakes, yes, during descent, but they also intentionally disrupt laminar airflow to reduce lift. And they can be deployed differentially, one side more than the other, for roll control during a turn.
Wow.
Even more advanced are stabilators, which combine the actions of a horizontal stabilizer and elevator. The whole tailplane moves.
The whole thing. Wow.
Yeah, offering greater pitch control authority rather than just moving a small control surface on the back edge.
No, it's not just fixed wing either. Rotary wing aircraft, helicopters, they have their own unique dynamics. I often wonder, watching them hover, it almost seems to defy logic. What stands out for you there is truly unique, maybe from a maintenance perspective?
For helicopters, the principles of hovering flight are absolutely paramount, unlike a fixed-wing aircraft.
Right.
A helicopter in a hover is constantly battling four forces that must be perfectly balanced. Lift and thrust, generated by the main rotor system, pushing straight up, must precisely equal the weight and drag pulling straight down. The pilot uses the collective pitch control, that lever usually on the left side of the seat,
Got it.
to change the angle of incidence of all the main rotor blades simultaneously. This directly controls the total lift and thrust, allowing vertical movement, up and down.
Okay.
For directional movement, forward, sideways, back, the pilot uses the cyclic pitch control. This actually tilts the tip path plane of the main rotor. It directs the total lift thrust force in the desired direction. Mechanically, this is incredibly complex, all these linkages.
I can imagine.
And let's not forget anti-torque systems, like the enclosed fenestron tail rotors you see on some types.
The fan and tail design.
Exactly. Or the no-tar system, the no-tail rotor system, which uses air pressure. Both counteracts the aerodynamic torque from the main rotor. Without them, the fuselage would just spin uncontrollably in the opposite direction.
Right.
So for AMEs, understanding the intricate linkages, the precise adjustments required for these systems is absolutely paramount. Even a small imbalance can have significant flight control consequences.
Okay. Moving from those invisible forces of air to the very tangible, let's talk about the aircraft's body itself. The structure. When we say primary structure, what exactly are we referring to, and why is its integrity so critical for an AME?
Primary structure is any portion of the aircraft that, if it fails, whether it's on the ground or in flight, would likely cause catastrophic issues.
Okay, so the really critical stuff.
The absolutely critical stuff. We're talking about things like loss of control, structural collapse, or even failure of a power unit leading to injury or loss of life. Examples: wing spars the main load-bearing members inside the wing. Engine mounts absorbing immense thrust and weight. Fuselage frames defining the body shape, bearing pressurization loads, even main floor structures. Within this, you have principal structural elements, or PSEs. These are specifically defined as elements carrying critical flight, ground, and pressurization loads. They're often also structurally significant items, SSIs, requiring special inspection and repair limitations because they are so critical.
For an AME.
For an AME, this means these are the areas demanding the most meticulous inspection, often specialized NDT methods, and very specific repair techniques defined by the manufacturer. No guesswork allowed.
So the integrity of these components is paramount. How do they actually build the main body, the fuselage, to withstand these incredible stresses?
Well, historically, there was the truss type. Think of early biplanes, a rigid framework of welded steel tubing, often covered with fabric.
Right, like a bridge structure.
Exactly. Incredibly strong for its weight, but not very aerodynamic for high speeds. More common today, especially for modern aircraft, is the monocoque, or single-shell design. This relies heavily on the strength of the skin itself to carry the primary loads, almost like an eggshell.
Interesting analogy.
But most modern aircraft actually use semi-monocoque construction. This is really a hybrid approach. It combines a stressed skin. The skin carries load with internal frames and stringers for reinforcement. It offers an optimal balance of strength, rigidity, and weight efficiency.
So the best of both worlds.
Pretty much. The frames provide the aircraft's cross-sectional shape, like ribs, and the stringers run lengthwise, providing stiffness and supporting the skin against buckling under compression. Even engine attachments are a key part of this structural puzzle. You have pylons, those support structures, extending forward and down from the wing spars. They're designed to absorb immense thrust and weight, securely attaching the engines on transport aircraft. Every part works together in this complex system.
And for maintenance, location is everything. You can't just say, oh, it's somewhere near the back. How do engineers and technicians know precisely where to find something in such a vast, complex structure?
That's a really important question, and it's critical for AMEs. How do you locate, say, fuselage frame station 137 or something, 50 inches right at the center line with absolute precision? Manufacturers use precise station numbering and zonal location systems. For instance, the very nose of the aircraft might be designated 0 station.
Yeah.
All other stations, like frames or bulkheads, are measured in inches after that point. So fuselage frame station 137 means exactly 137 inches after the nose reference point.
Okay, makes sense.
Similarly, for lateral location, the aircraft's center line might be the 0 station, with measurements taken to the right or left, often called buttock lines or water lines for vertical location. It's absolutely critical, though, to always consult the specific manufacturer's aircraft maintenance manual, the AMM, because these systems aren't always uniform across different aircraft types.
Good point. Always check the manual.
Always. What's also critical for AMEs are the system installation provisions. Designers have to consider ease of access for regular maintenance. Things like fluid checks, filter changes, or replacing line-replaceable units, LRUs. Efficient access directly saves time, reduces the chance of human error, and lowers operating costs for the airline. It makes your job not just easier, but also faster and more accurate. Good design considers maintenance from the start.
And speaking of critical, sometimes small details, static dischargers, those little wicks you see trailing off the wings and tail, what role do they play in flight safety, and what's the AME's perspective on them?
Static dischargers, or static wicks, those flexible or semi-flexible devices. Their primary function is to dissipate electrical energy safely back into the atmosphere. This could be energy from lightning strikes, or just static electricity building up as the aircraft flies through the air, especially through precipitation or clouds. This dissipation is vital to prevent potential arcsing between different parts of the aircraft structure. And critically, it prevents the ignition of fuel vapors, especially around fuel tank vents during refueling or even in flight. If all the bonding devices, the straps and connections ensuring electrical continuity across the entire airframe with resistance not exceeding 0.1 ohm are intact,
0.1, okay,
then lightning energy can dissipate relatively safely over the entire surface, preventing dangerous potential differences from building up. For an AME, regular inspection of these wicks for damaged broken strands, missing wicks, and ensuring all bonding straps are intact and secure is a fundamental maintenance task. It's often overlooked, but absolutely crucial for safety.
The core system's power, control, and communication.
Okay, from static electricity to the very power that runs the aircraft, electrical systems are absolutely foundational. Without power, you're not going anywhere, and you're certainly not operating anything critical. Let's start with batteries. What does an AME need to know about these critical power sources?
Right, batteries, they're electrochemical energy storage devices, basically portable power plants for startup or emergency use. You have primary cell batteries, like typical dry cells. These are non-rechargeable. Trying to reverse their chemical reaction by charging them isn't just futile, it's usually dangerous.
Right. Don't try charging those.
No, it can even lead to an explosion because the metal components inside are actually consumed during discharge. Then you have secondary batteries, which are rechargeable, like lead-acid batteries, which come in flooded or vented types that need electrolyte checks,
The older style.
and valve-regulated or sealed VRLA types, which are lower maintenance. Nickel-cadmium or nitride batteries are also common rechargeable and known for high power output. Lithium-ion batteries are increasingly common in modern aircraft. Why? Significantly higher energy density, more power for less weight and size.
That's a big advantage in aviation.
Huge. But there's a caveat. They require specific safety devices built in, like cell monitoring circuits, and absolutely strict adherence to manufacturer instructions for charging and temperature monitoring. This is to prevent overheating and thermal runaway. That's a self-sustaining chemical reaction that can generate intense heat and potentially lead to fire if not managed properly.
So for an AME, precise procedures are non-negotiable.
Absolutely non-negotiable. Handling and charging require specific training and equipment.
Okay, once airborne, the aircraft needs its own continuous power generation. How does that work, especially given the demanding and fluctuating environment of flight?
So DC power, mainly for smaller aircraft systems or specific components, is often generated by engine-driven DC generators. These are controlled by voltage regulators that continuously monitor the system voltage and maintain a specific range, say 13.5 to 14.5 volts, even as the engine RPM changes. Some older designs might use vibrating type regulators that literally open and close contact points rapidly to average the generator's field magnetism and keep the voltage stable.
Fascinatingly mechanical.
Yeah, old school, but effective. AC power, though, is more prevalent in large aircraft. It's more efficient for transmission over long distances and used for many motors. It comes from AC alternators. These are often integrated into constant speed drives, CSDs, or integrated drive generators, IDGs.
GSDs and IDGs, right?
These devices, mechanically or electronically, ensure a stable 400 Hz frequency, which is the standard for aircraft AC power, regardless of changes in engine RPM. That consistency is vital for sensitive avionics.
And backups.
Absolutely. Auxiliary power units, APUs, provide power on the ground for systems and air conditioning and can act as an emergency backup generator in the air. And in critical emergencies, ram air turbines, or RATs, can be deployed into the airstream. They spin a small turbine using airflow to generate crucial backup hydraulic and/or AC power.
The RAT, a last line of defense.
A critical one.
Okay, distributing all that power throughout the aircraft must be incredibly complex. You've got hundreds of circuits, components, all needing a precise supply. How is it managed?
It is incredibly complex. Modern aircraft use computerized control units, typically located in equipment bays, to regulate and distribute AC power. Take the bus power control unit, or BPCU for example. It monitors the entire electrical system using remote current transformers, or CTs.
CTs?
Yeah, they're like clamps that go around the main power cables. They induce a voltage directly related to the current flowing through the cable, but without making direct electrical contact. It's safer and simpler.
Clear.
The BPCU uses this info and communicates with generator control units, GCUs, to ensure everything's operating correctly. Voltage, frequency, load sharing. Power distribution typically uses split bus, parallel bus, or split parallel systems, all designed with multiple layers of redundancy.
Redundancy is the key word again.
Always. A split bus system, for instance, ensures generators remain isolated, powering their own set of buses, but they can share loads or power any given bus independently if needed through bus tiebreakers. A parallel bus system allows multiple generators to connect together and share the entire AC load. This requires them to be perfectly synchronized, same voltage, same frequency, and crucially, in phase. It's a sophisticated feat.
Wow.
And the ability for the APU or the RAT to automatically provide backup power if the main generators fail is a critical safety feature, ensuring vital flight controls and instruments remain operational no matter what.
What about converting power types? You mentioned AC and DC flying around. How do they talk to each other, and what's the practical implication for an AME?
Good question. You need converters. Inverters convert DC power to AC power. Older types were rotary inverters, basically a DC motor spinning an AC generator. But static inverters, using semiconductors, are much more common today. They're preferred due to higher efficiency, smaller size, less maintenance, and better compatibility with modern electronics. Transformers, on the other hand, change AC voltage levels. They only work with AC because they're relying on a changing magnetic field. This is crucial for efficient power transmission. Over distances, you step up the voltage for transmission, reducing current and power loss, then step it down where it's needed for components.
Makes sense.
And rectifiers convert AC into pulsating DC. This is essential for charging batteries and powering many aircraft electronic components that need DC. Advanced rectifiers like silicon-controlled rectifiers, or SCRs, are particularly interesting. They allow very precise control over power delivery. Think about lighting dimming systems. Instead of using inefficient resistors that just waste power as heat, SCRs can manage exactly when current flows during each AC cycle, effectively controlling the average power delivered with much less heat generation.
That's quite sophisticated.
It is. For an AME, understanding these conversions DC to AC, AC to AC, AC to DC is key for troubleshooting. When you have a power issue, you need to be able to trace it from the source through any converters to the affected component.
Okay, from power, let's move to how that power translates into precise control of the aircraft. Beyond the basics of ailerons, elevators, rudders, what's interesting and important about flight controls for an AME's daily work?
Well, the primary controls are fundamental, obviously. But think about the subtleties. Many aircraft, especially swept-wing jets, use yaw dampers. These automatically counteract a tendency called Dutch roll. It's a sort of wallowing side-to-side oscillation, a combination of yawing and rolling.
Uncomfortable for passengers, I imagine?
Very uncomfortable, and in extreme cases, it can put stress on the airframe. The yaw damper smooths this out, crucial for comfort and structural integrity. And beyond the basic movements, those high-lift devices we mentioned, flaps, slats, they significantly impact takeoff and landing performance. These aren't just extra surfaces, they dynamically change the wing's shape and area. For an AME, this means maintaining the complex mechanisms, tracks, actuators, sensors that allow these surfaces to extend and retract precisely.
Right, it's not just bolting on a part.
Not at all. And things like lift dumpers or ground spoilers, which deploy automatically on landing, and speed brakes used in flight, they all fall into this category. You're ensuring the precision of these intricate systems that manage the very airflow over the wing.
I always find the feel of the controls fascinating, especially in larger aircraft where there's often no direct mechanical link.
Yeah.
How does the pilot get that crucial feedback? How do they know how much force they're applying?
That's where artificial feel systems come in. They're vital in aircraft with hydromechanical or especially electromechanical or fly-by-wire controls. In these systems, the pilot isn't directly feeling the aerodynamic loads pushing back on the control surfaces through cables.
Right, the hydraulics are doing all the heavy lifting.
Exactly. So for AMEs, the key insight here is that you're maintaining a critical feedback loop to the pilot. These artificial feel systems use various mechanisms, maybe springs, hydraulic units, or complex cams, like a spring-loaded roller riding on a specially shaped cam, creating resistance that increases as the pilot moves the controls further. This simulates the aerodynamic resistance, preventing pilots from inadvertently overstressing the aircraft by applying excessive force without realizing the actual loads involved. A fault in this system isn't just a gauge issue. It can lead to pilots making dangerously large control inputs or losing that crucial intuitive sense of flight control forces. It's where the pilot's perception meets the machine's reality.
That's a critical link.
Very critical. Another important aspect, especially at high speeds, is Mach trim. This automatically adjusts the stabilizer or elevator to counteract Mach tuck.
Mach tuck.
Yeah, it's a nose-down tendency that occurs as the aircraft approaches its critical Mach number. As shock waves form on the wing, the center of pressure moves aft, causing the nose to want to pitch down. Mach trim compensates for this.
And that relates to the coffin corner.
It does, yeah. Think of a graph plotting altitude against speed. At high altitudes, the air is thin. To generate enough lift, you need to fly faster, pushing you closer to your critical Mach number, the speed where airflow over parts of the wing goes supersonic, causing drag rise and control issues. At the same time, because the air is so thin, your stall speed also increases. You need more speed to avoid stalling. So your safe operating window, that margin between stalling at the low end and hitting Mach buffet or losing control at the high end, becomes incredibly narrow.
Like being trapped in the corner of the graph.
Exactly, like being trapped in a coffin corner. It makes stable flight extremely challenging, demanding precise control, which these trim systems help provide.
And safety on the ground is just as important as in the air. What are gust locks, and why are they a simple but vital part of an AME's routine?
Absolutely. Gust locks are used to secure flight control surfaces when the aircraft is parked. They prevent strong winds from causing the surface ailerons, elevators, rudders to flap violently back and forth.
Which could cause damage.
Significant damage, yeah. To the surfaces themselves, the hinges, or the control linkages inside. Gust locks can be external devices that physically restrain the surfaces, often with bright "remove before flight" flags.
Seen those.
Or they can be integral mechanisms in the cockpit that restrict the movement of the control column or pedals. For an AME, checking that these are properly engaged when an aircraft is parked, especially in windy conditions, and ensuring they are removed before flight, is a simple but crucial step to prevent costly damage or, worse, a flight control issue on takeoff.
But the big shift, the real revolution in modern aircraft, is fly-by-wire. This completely changes the interaction between the pilot and the control surfaces. Let's unpack this. How does it work, and what are the implications for maintenance?
Yeah, here's where it gets really interesting and really different. Fly-by-wire, or FBW, systems fundamentally replace those traditional mechanical linkages, cables, pulleys, push rods, with electrical signal.
Wires instead of cables.
Exactly. The pilot's control inputs, from a wheel or a side stick, are converted into electrical signals. These signals are transmitted through multiple redundant flight control computers. These computers then command hydraulic actuators that actually move the control surfaces. This design significantly reduces aircraft weight, getting rid of all that heavy mechanical linkage.
Makes sense.
It also lowers maintenance costs associated with mechanical systems, lubrication, tensioning, wear and tear, and dramatically improves reliability because electronic components tend to be more reliable than complex mechanical systems. But the biggest innovation, really, is the intelligence in the system. The computers are continuously programmed with the aircraft's flight characteristics, its flight laws.
Flight laws?
Yeah, software rules that define how the aircraft should respond. The computers can adjust the control movements to ensure consistent aircraft response across all flight conditions: speed, altitude, weight, configuration. They are also crucial for preventing undesirable or dangerous characteristics. They can be programmed to limit bank angle, angle of attack to prevent stalls, or prevent overspeeding. Flight envelope protection.
So the computer acts as a safety net.
A very sophisticated safety net. In fact, many later generation military high-performance aircraft are designed to be inherently aerodynamically unstable for extreme maneuverability. They literally cannot be flown without FBW computers constantly making micro-adjustments thousands of times per second just to keep them stable.
Wow.
So in an FBW system, pilot input wheel or side stick gets converted into electrical signals, processed by flight computers. Computers direct electrohydraulic valves. These valves precisely control hydraulic fluid flow to the actuators that move the control surfaces.
And feedback. How does the system know the surface moved correctly?
Critical part. Feedback loop. Linear variable displacement transducers, LVDTs, or similar sensors within the actuators send signals back to the computer telling it the exact position and rate of movement of the actuator. The loop is closed. And redundancy, again, is absolutely key. Multiple independent computers, often dissimilar hardware and software, multiple independent hydraulic systems powering actuators, multiple electrical buses, multiple sensors, all performing the same function simultaneously.
Fail operational.
Fail operational capability. If one system or channel fails, another immediately takes over without any interruption to flight control. Often, systems use voting logic. If one computer disagrees with the others, its input is ignored.
So for an AME, this means troubleshooting shifts significantly.
Hugely. You're moving from inspecting cables and checking rigging tensions to diagnosing complex computer signals, understanding software logic, using specialized test equipment to check data buses and LRUs. It's a different skill set, blending mechanical and avionics expertise.
Okay, let's talk about the flight deck. That hub of information, the nerve center. How do aircraft instruments translate raw data pressure, temperature, magnetic fields into something meaningful, something that guides the crew safely?
Right, instruments. Broadly classified by function. Navigation, engine monitoring, and flight instruments.
Yeah.
Many of these rely heavily on pressure measurements. Devices like Borden tubes, those are C-shaped or coiled flattened tubes that tend to straighten out as pressure inside increases. Good for high-range liquid and pneumatic pressure, like hydraulics or oxygen tanks. Then you have diaphragms, aneroids which are sealed, evacuated diaphragms, very sensitive to changes in atmospheric pressure, used in altimeters and bellows. All these convert pressure changes into mechanical movement. This movement can directly drive an instrument pointer on order gauges, or more commonly now, it moves a transducer, something that converts mechanical movement into an electrical signal.
Ah, the transducer is the key link to digital systems.
Exactly. That electrical signal is then sent to a cockpit display or a computer for processing and display. This applies to critical engine parameters like fuel pressure, oil pressure, but also to crucial air data, airspeed, altitude, vertical speed.
Air data, especially altitude and airspeed, are incredibly critical for flight safety and navigation. How are these sensed and interpreted?
Indeed. The pitot-static system is the primary source here. You have a pitot tube, usually sticking out facing directly into the airstream, to capture impact air pressure, also known as ram air or total pressure.
Right, you see those on the nose or wings.
Simultaneously, you have static ports, which are flush openings on the side of the fuselage, located where the airflow is relatively undisturbed. They measure the ambient atmospheric pressure, the static pressure. These two pressures, pitot and static, are then plumbed to the three key instruments. The airspeed indicator, which calculates speed based on the difference between pitot and static pressure, dynamic pressure.
Okay, the difference is key.
The altimeter, which measures altitude based on the absolute static pressure decreasing as you climb, and the vertical speed indicator, or VSI, which detects the rate of change of static pressure to show your rate of climb or descent.
Got it.
Altimeters, for example, need precise pressure settings input by the pilot, like QNH, which gives altitude above mean sea level, QFE for height above the airfield, or QNE, the standard pressure setting of 29.92 inches of mercury, or 1030-13.2 millibars, used above transition altitude to compensate for weather variations and display accurate altitude information.
Lots of altitudes.
Yeah, pressure altitude, density altitude, indicated altitude, true altitude. They all mean different things. The VSI, especially in instantaneous VSI, or IVSI, uses a clever diaphragm and calibrated leak mechanism. It essentially compares the current static pressure with the slightly delayed pressure inside its case. Any change in static pressure shows up immediately as a climb or descent indication.
Okay.
Now, for high-performance aircraft, this gets more sophisticated. Air data computers, ADCs, or digital air data computers, DADCs, take these raw pitot and static pressures, and also temperature input, and they electronically process them. They compensate for factors like air compressibility at high speeds, temperature effects, and installation errors to provide highly accurate, corrected air data calibrated airspeed, true airspeed, Mach number, altitude, vertical speed to various other aircraft systems like the autopilot, FMS, and flight displays.
Temperature is another vital parameter you mentioned, especially for engine performance and those air data calculations. How's that measured?
Temperature is measured using several methods. Bimetallic strips are simple, two different metals bonded together. As temperature changes, they expand at different rates, causing this strip to bend. This movement can drive a pointer.
Okay.
Ratiometer systems use changes in electrical resistance within a temperature-sensitive probe, usually part of a Wheatstone bridge circuit. The imbalance in the bridge indicates the temperature. And thermocouples are very common, especially for high temperatures like engine exhaust gas temperature, EGT. They use the principle that heating a junction of two dissimilar metals generates a small voltage, an electromotive force, that's proportional to the temperature difference between that junction and a reference junction.
Right.
Total air temperature, or TADE probes, are particularly important for performance calculations. These are specially designed probes that accurately capture the outside air temperature plus the temperature rise due to the air being compressed as it hits the aircraft at high speed, the ram rise effect.
So it's the effective temperature the aircraft feels.
Exactly. That TAT value is crucial for engine performance calculations, determining true airspeed and managing systems like ice protection.
And fuel quantity. Definitely not a dipstick anymore on large aircraft. How do they measure fuel accurately in those complex, shifting tanks?
Far from it. Modern systems, especially in transport category aircraft, typically use capacitance-type fuel quantity indicators. Big advantage. No moving parts inside the tanks.
More reliable.
Much more reliable, less prone to sticking or damage. They use variable capacitance transmitters, essentially fuel probes, installed vertically inside the tanks. These probes act like capacitors. Fuel and air have different dielectric constants. Fuel is a better insulator than air. So as the fuel level changes, covering more or less of the probe, the overall capacitance of the probe changes in direct proportion to the fuel volume. These capacitance values from all the probes in a tank are then electronically measured, compensated for fuel density and temperature, and totaled by a microchip computer, often integrated into the indicator or a central processor. The result is displayed digitally in the cockpit, usually in pounds or kilograms, with very high accuracy. It's a significant improvement over older mechanical float or ratiometer systems, crucial for fuel management, range calculation, and weight and balance.
Gyroscopes. They seem like older technology, spinning wheels, but they're still fundamental in many instruments, right? How do these spinning wheels translate into stable flight information?
Absolutely. Mechanical gyroscopes basically precisely balance wheels or rotors with mass concentrated around their perimeter, spinning at very high speeds are indeed at the heart of many traditional flight instruments. They rely on two key physical principles. First is rigidity in space, or gyroscopic inertia. A spinning gyro strongly resists any attempt to change its plane of rotation. It wants to stay pointing in the same direction in space, regardless of how its base, the aircraft, moves around it.
Okay. Stability.
Exactly. This principle is used in attitude indicators, or artificial horizons, which show the aircraft's pitch and roll relative to the horizon, and also in heading indicators, or directional gyros, TGs, which maintain a set heading. The second principle is precession. If you apply a force trying to tilt the spin axis of a gyro, it doesn't tilt in the direction of the force. Instead, it responds with a tilting motion 90 degrees away from the applied force in the direction of rotation.
That's counterintuitive.
It is, but it's predictable. This precession is utilized in turn coordinators, which use a tilted gyro to sense both rate of roll and rate of yaw, giving an indication of the turn quality. Now, older aircraft might use vacuum-driven gyros, spun by air sucked over vanes on the rotor, often with caging devices to manually erect them or lock them before shutdown.
Right.
But modern systems almost universally use electric gyros, often sealed units. And increasingly, these are being replaced by solid-state devices like ring laser gyros or MEMS gyros found in attitude heading and reference systems, AHRS, or inertial reference systems, IRS. These feed precise attitude and heading data into the glass cockpit displays.
Speaking of glass cockpits, the way information is presented has totally transformed. For an AME, what's the significance of this digital shift on the flight deck? How does it change things?
It really has. Electronic displays, like those in EFIs, electronic flight instrument systems, which include the PFD, primary flight display, showing attitude, speed, altitude, and the ND navigation display showing the map, route, weather in EICAS, engine indication and crew alerting system, or ECAM, electronic centralized aircraft monitor. In Airbus, these use symbol generators or display management computers. These powerful computers take data from various sensors and systems, process it, and create the complex graphical symbology displayed to the pilots. These systems are typically designed with high levels of redundancy, often triple redundant computers and power supplies. This allows for automatic reversionary modes. If a computer or display unit fails, the system automatically reconfigures to ensure the most critical information, like attitude, airspeed, altitude from the PFD, is still displayed, perhaps moving it to another screen.
So built-in backup plans.
Exactly. For example, if an outboard display unit fails, essential flight information will automatically switch over to an inboard display, like the ND or MFD. Flying the aircraft always takes priority. This resilience is absolutely critical for flight safety. For an AME, it means understanding not just the displays themselves, but the complex network of computers, data buses, and sensors that drive them, and how to use built-in tests by LD to diagnose faults.
Beyond just flight information, there are crucial warnings and monitoring systems, vital for catching potential issues before they become catastrophic emergencies.
Absolutely vital. Think about engine vibration monitoring systems. They use piezoelectric transducers, accelerometers mounted on engine sections. These convert mechanical vibrations into electrical signals. The signals are processed and displayed as vibration amplitude, often on the EICAS or ECAM screen. High vibration can be an early warning of a potential mechanical failure, like a failing bearing or a cracked turbine blade, allowing maintenance action before it leads to an engine shutdown.
Proactive maintenance.
Exactly. Aircraft also have centralized warning systems. Master warning lights, usually red, demanding immediate attention, and master caution lights, usually amber, for less urgent advisories, are typically located prominently on the glare shield panel, right in the pilot's line of sight. These are interconnected with specific system annunciator lights, often on an overhead panel. They might be triggered by fault pulsars and SCR circuits, or increasingly by digital logic and system computers.
And GPWS.
Ground Proximity Warning Systems, GPWS, or the enhanced version eGPWS with terrain databases, are critical safety nets. They use radio altimeter data, GPS position, and internal databases to provide alerts for potentially hazardous situations relative to the ground. They have different modes, giving distinct oral warnings like too low, terrain, sink rate, don't sink after takeoff, or glide slope if deviating below the ILS path. They provide visual and urgent oral alerts to prevent controlled flight into terrain or see if I had a major cause of accidents in the past.
And getting the aircraft's true heading is essential for navigation. It seems simple, like a basic compass, but it's often linked to more complex remote compass systems, isn't it?
It is. While a simple magnetic standby compass is usually required, Primary heading information often comes from remote indicating slave gyro compasses. Specifically, flux gate compasses are common. These systems augment the stability of a gyroscopic direction indicator with magnetic direction information from the Earth's field. A flux valve, or flux gate, often located in a wingtip or tail area, away from magnetic interference, detects the direction of the Earth's magnetic field lines.
How does it do that?
It typically uses core material that's easily saturated magnetically, excited by an AC current. The Earth's field influences how this core saturates. Pickup coil windings around it sense these changes and send electrical signals to the compass system. This system then slaves the gyroscopic heading indicator to the magnetic heading, providing a stable, deviation-free magnetic heading display in the cockpit. It overcomes the turning and acceleration errors and the inherent fluctuations of a traditional direct-reading magnetic compass, ensuring accurate and reliable heading information for navigation and autopilot systems.
Okay, let's shift gears to communication and navigation, the systems that connect the aircraft to the outside world and tell it where it's going. Aircraft aren't just flying machines, they're complex communication and navigation hubs. Let's talk about the invisible waves that make it all possible.
Right, the fundamentals of radio wave propagation are key for an AME working on these systems. Understanding things like wavelength, the physical distance of one wave cycle.
Shorter wavelength means higher frequency.
Exactly. Frequency, the number of cycles per second measured in hertz. And the vast radio frequency spectrum from very low frequency, VLF, up through HF, high frequency, VHF, very high frequency, UHF, ultra high frequency, and microwaves. Generally, aircraft comms use HF, VHF, and UHF bands from around 2 MHz up to the GHz range for things like GPS and satellite comms. Crucially, though, by themselves, radio waves, the carrier waves, don't carry information. They're just oscillating energy. This is where modulation comes in. Modulation is the process of varying some characteristic of the carrier wave, its amplitude, AM, its frequency, FM, or its phase, PM, in order to encode the information like voice or data onto it.
So you piggyback the information onto the carrier.
Precisely. When you modulate a carrier, you create sidebands. These are additional frequencies generated above and below the main carrier frequency, and they actually contain the information being transmitted. The bandwidth is the total range of frequencies occupied by the modulated signal of the carrier plus its sidebands. For example, in standard AM voice communication, if you modulate a carrier with voice frequencies up to, say, 3 kHz, you'll create sidebands extending 3 kHz above and 3 kHz below the carrier, resulting in a total bandwidth of 6 kHz.
So how do these principles translate to actual aircraft communication systems, and what are the practical differences for an AME working on them?
Well, the primary system for air traffic control and general air-to-ground voice communication is VHF radio. VHF comm radios operate in the very high frequency band, typically 118.0 MHz to 136.975 MHz. In many regions like Europe, they use 8.33 kHz channel spacing now, instead of the older 25 kHz, to create more available channels within that band.
Packing more channels in.
Exactly. VHF is strictly line-of-sight propagation, meaning its range is limited by the curvature of the Earth, and antenna height typically may be 150, 200 miles for an aircraft at high altitude talking to a ground station. And it uses amplitude modulation, AM. For long-range communication, especially over oceans or remote areas where VHF won't reach, aircraft use HF radio. High frequency.
HF bounces off the ionosphere, right?
Correct. HF waves, roughly 2 to 30 MHz, can refract or bounce off the ionosphere, allowing communication over thousands of miles, well beyond the horizon. HF systems operate in simplex mode, transmit or receive, but not both at once, or half duplex. They often use more efficient modulation techniques like single sideband, SSB, which suppresses the carrier in one sideband to save power and bandwidth.
And HF needs antenna tuning.
Yes, critically. Because HF covers such a wide frequency range, the antenna system must be tuned to resonate efficiently at the specific frequency selected for transmission. This is done automatically by an antenna coupler or tuner unit. You'll often hear a tone in the headset while it's tuning. For an AME, this means understanding antenna couplers, grounding, and the specific characteristics of HF systems compared to VHF.
And getting the message across isn't just about the radio waves, it's also the audio system itself, the interface between the crew, the radios, and the passengers.
Absolutely. The audio system integrates all the sound sources and outputs. Key components include the Audio Integration System, or AIS, Remote Control Audio Units, or RCAU, and the Audio Control Panels, ACPs, in the cockpit. The ACP allows each pilot to select which radios they want to transmit on and listen to, adjust volumes, and select between interphone, INT, for internal crew communication, and radio, RAD, for external comms.
That infrared switch is pretty important.
Crucial. Even seemingly minor components like jackbox consoles for ground crew communication or the push-to-talk, PTT, switches on the control columns or yokes, are vital parts of the system. Interestingly, on some aircraft, there are potentiometers under the PTT button cover for adjusting microphone sensitivity and side tone volume.
Good tip for AMEs.
Yeah, and the Cabin Intercommunication Data System, CIDS, extends this communication network to the cabin for flight attendants, managing passenger air, PA systems, attendant calls, and sometimes even interfacing with entertainment systems and cabin lighting. It's a complex digital network in modern aircraft.
Of course, critical for post-incident analysis are the black boxes. We hear about them all the time in the news after an accident. What are they really, and why are they so vital?
Indeed. The term black box actually refers to two or sometimes one combined crucial devices: the cockpit voice recorder, CVR, and the flight data recorder, FDR. But first, let's mention the emergency locator transmitter, or ELT. This is a separate device, usually installed far aft in the fuselage, near the tail.
For survivability.
Exactly. It's designed to activate automatically in a crash, triggered by a G-force sensor, and transmit a distress signal on specific emergency frequencies. Modern ELTs transmit on 406 MHz. This is a digital signal monitored by satellites, and it can include the aircraft's unique registration information and, if connected to GPS, its precise location, allowing rescue crews to pinpoint the site within about 100 meters.
Huge improvement over older ones.
Massive improvement over the older 121.5 MHz analog ELTs, which relied on line-of-sight reception and were harder to locate accurately. The 406 MHz system also transmits on 121.5 for local homing. Maintenance includes annual inspections and operational tests, crucially. These tests should only be done the first 5 minutes past the hour to avoid triggering false alarms in the satellite system.
Okay, back to the CVR and FDR.
Right. Despite being called black boxes, they are actually painted bright international orange and covered in reflective tape to make them easier to find in wreckage.
Orange boxes, then.
Pretty much. They're usually located together in the tail section, again, for maximum crash survivability, as it's often the part of the aircraft that sustains the least impact damage. The CDR records all audio in the cockpit pilot voices via microphones, radio transmissions, ambient sounds, typically for the last 2 hours of flight, constantly recording over the oldest data on a loop. The FDR records a vast number of aircraft parameters. Older ones recorded maybe a dozen, but modern FDRs capture hundreds, sometimes over 1,000 parameters.
Like what?
Airspeed, altitude, heading, vertical speed, engine parameters, RPM, temperature, fuel flow, flight control positions, aileron, elevator rudder, flaps, spoilers, hydraulic pressures, autopilot status, navigation data, switch positions. Basically a comprehensive digital snapshot of the aircraft's state and how it was being flown.
How long does it record for?
Modern FDRs typically record for up to 25 hours, again, on a continuous loop, operating automatically from before takeoff until several minutes after shutdown. The data recovered from these CVRs and FDRs is absolutely crucial for accident investigators to piece together the sequence of events and determine the probable cause. Sometimes they are housed together in a single combination recorder unit.
Moving to navigation, how do aircraft find their way from A to B across vast distances and through complex airspace? What are the core systems?
Well, one of the older systems still around is automatic direction finding, or ADF. It uses ground-based non-directional beacons, NDBs. The aircraft has loop and sense antennas.
Loop and sense.
Yeah, the loop antenna detects the direction of the signal, but it has ambiguity. It could be pointing towards or away from the station. The sense antenna resolves this ambiguity. The ADF indicator in the cockpit simply points towards the NDB station, giving a relative bearing.
Okay, simple point and go.
Pretty much. More precise for approaches is the Instrument Landing System, or ILS. This provides both lateral, left, right, and vertical up-down guidance to align the aircraft with the runway centerline for landing. It uses ground-based transmitters. The localizer provides the horizontal guidance, operating on VHF frequencies, 108 to 111.95 MHz, odd tenths. It transmits two overlapping lobes modulated at 90 Hz and 150 Hz. The receiver compares the strength of these signals to show deviation left or right on the PFD or ILS indicator.
Okay.
The glide slope provides the vertical guidance, operating on paired UHF frequencies, 329.3 to 335.0 MHz. It works similarly with 90 Hz and 150 Hz modulated lobes to define the correct descent path, usually around 3 degrees, displayed as up-down deviation.
And flight directors.
Flight director systems, FDSs, integrate this ILS information, plus attitude, heading, and airspeed data. They compute and display command bars, like crosshairs, on the attitude indicator, showing the pilot the precise pitch and roll attitude required to intercept and follow the desired flight path, like the ILS beams. It's essentially telling the pilot how to fly the aircraft to achieve the desired outcome. It's like an autopilot display without the servos actually moving the controls.
And for precise distance, essential for knowing exactly where you are along the route or on approach.
That's where distance measuring equipment, or DME, comes in. DME is a radio navigation aid that measures slant range distance. The aircraft sends out interrogation pulses on a specific UHF frequency, 962, 1213 MHz. A ground station, often co-located with a VOR or ILS, receives these pulses and, after a precise delay, transmits reply pulses back on a different frequency. The aircraft's DME receiver measures the round-trip time of these pulses and calculates the distance based on the speed of light. It's displayed directly in nautical miles. And flight management systems, FMSs, are the real brains of modern navigation. These are highly advanced computers, often dual or triple redundant. They integrate data from multiple sources: air data computers, inertial reference systems, IRS, GPS receivers, VORD-AME receivers. They contain vast navigation databases with airports, waypoints, airways, procedures.
Everything.
Pretty much everything. The FMS computes the optimum flight path, provides guidance cues, automatically tunes navigation radios, monitors fuel consumption against the flight plan, calculates performance data, constantly recalculating based on real-time conditions like winds. They also provide BITE, built-in test equipment information, which is invaluable for maintenance personnel to quickly identify faulty LRUs.
GPS is so common now, in our cars, our phones, but what's its role in aviation beyond just giving a basic position fix? How does it achieve the incredible precision required for flight, especially for landings?
All right, so standard GPS on its own isn't quite accurate or reliable enough for all phases of flight, especially precision approaches. That's where augmentation systems come in. Systems like EASA, the Wide Area Augmentation System, used primarily in North America. EASA uses a network of widely spaced ground reference stations that monitor GPS satellite signals. They detect errors in the signals caused by atmospheric disturbances or satellite clock drift.
Okay.
These error corrections are then uplinked to geostationary satellites, which broadcast them back down to WAAS-enabled GPS receivers in aircraft. This significantly enhances both the accuracy and, crucially, the integrity, the trustworthiness of the GPS position, allowing for certain types of GPS-based approaches, LPV approaches. GBA's ground-based augmentation system provides even higher precision, but locally, right at an airport. It uses ground receivers at the airport to detect errors and transmits corrections directly to approaching aircraft via a VHF data broadcast, or VDB, data link. This enables GNSS landing system approaches, which can potentially offer Category 1, 2, or even 3 precision, similar to ILS, but with more flexibility in approach path design. For example, Boeing aircraft often use multi-mode receivers, MMRs, that can handle ILS, basic GPS, and can be upgraded to support GLS using GBA's data. For an AME, maintaining the integrity of these GPS antenna systems and ensuring the receivers have the correct software and databases is paramount.
And for traffic management, keeping planes safely separated. Beyond traditional ground-based radar, how are aircraft seeing each other and being seen more effectively?
Well, the foundation is the transponder. Mode A transponders just reply with a 4-digit identification code assigned by ATC. Mode C adds pressure-altitude reporting, derived from the aircraft's altimeter, or ADC. Mode S is more advanced, allowing selective interrogation and data link capability. Pilots need to know the critical special purpose code 7700 for emergency, 7600 for communication failure, 7500 for unlawful interference or hijacking. Setting these alerts ATC immediately.
Got it.
But the real game changer is ADS-B, Automatic Dependent Surveillance Broadcast. With ADS-B out, the aircraft automatically broadcasts its precise position, derived from its own GPS, altitude, velocity, identification, and other data, typically once per second, to other ADS-B-equipped aircraft, ADS-B, and ground stations.
So it's broadcasting its position, not waiting to be asked by radar.
It's dependent because it relies on the aircraft's own navigation systems, mainly GPS, but it's automatic and broadcast. This offers significant advantages over traditional radar, which relies on sweeping radio beams and interpreting reflections. ADS-B provides lower-cost infrastructure, much higher accuracy and update rates, isn't affected by terrain blockage like radar can be, works better in adverse weather, and allows for higher traffic density and more efficient routing. It's fundamental to next-gen air traffic modernization.
And MLS, is that still relevant?
Microwave landing systems, MLS, were developed as a potential successor to ILS, offering advantages like multiple approach paths, including curved and segmented approaches, and being less susceptible to interference. It works differently, using precise time intervals of scanning to and fro pulses in azimuth and elevation to determine the aircraft's angular position relative to the runway. Precision DME, DMEP, is often coupled with MLS for highly accurate distance information. While it hasn't replaced ILS globally as once envisioned, MLS is used at some airports, particularly where ILS performance is problematic, and it remains a system AMEs might encounter.
Inertial navigation systems, INS, or the modern inertial reference systems, IRS. What's their role, especially now with GPS being so ubiquitous? Are they still needed?
Absolutely needed. INS or IRS are completely self-contained navigation systems. They don't rely on any external radio signals like GPS or VRDME.
How do they work, though?
They use a combination of gyroscopes, either mechanical spinning mass, ring laser gyros, or fiber optic gyros, to maintain a stable reference platform or mathematically track orientation, and highly sensitive accelerometers to measure every tiny acceleration the aircraft makes forward, sideways, up, down. Starting from a known initial position, entered by the pilot before flight during alignment, the system continuously integrates these measured accelerations over time to calculate velocity, and then integrates velocity over time to calculate the change in position. It constantly updates the aircraft's latitude and longitude, altitude, heading, and attitude.
Wow, all internally calculated.
All internally. While GPS is incredibly accurate most of the time, INSERS provides a crucial, independent, highly accurate backup. It's completely immune to GPS jamming or signal loss, essential for navigating over remote areas with no ground-based aids or during potential GPS outages. Modern systems often blend IRS and GPS data for the best possible accuracy and integrity. For an AME, the alignment process and monitoring the health of the IRS units are key maintenance aspects.
And for automated reporting, you mentioned ACARS earlier. How does that fit into the communication picture?
Right. ACARS originally AME communication addressing and reporting system, developed back in 1978. It's essentially a digital data link system for transmitting short text messages between the aircraft and ground stations, like airline operations centers, via the aircraft's existing VHF or HF radios, or sometimes satellite communication links. A primary function is automating the transmission of key flight progress times, the UOI times, out of the gate, off the ground, takeoff, on the ground landing, and in the gate arrival.
Oh, I got it.
This is done using discrete inputs from sensors like parking brakes, landing gear squat switches, weight on wheels, and sometimes cabin doors. This significantly reduces crew workload compared to making voice reports, provides more accurate and timely operational data to the airline, and facilitates things like engine health monitoring reports transmitted automatically in flight. It was really a pioneering example of data linking in aviation, streamlining information flow. For an AME, understanding ACARS messages displayed on a maintenance terminal can sometimes be a shortcut to diagnosing a system fault reported by the aircraft itself.
The environment and maintenance comfort, safety, and troubleshooting.
Okay, being cooped up in a metal tube at 35,000 feet could be incredibly uncomfortable, even dangerous, without the environmental control systems. How do aircraft manage the cabin environment, keeping passengers comfortable and, importantly, safe with breathable air?
Absolutely vital systems. Air supply for the cabin and general conditioning usually comes from engine bleed air. That's very hot, high-pressure air tapped directly from the engine's compressor section.
Bleed air, right.
On the ground, or as a backup in the air, this air can also come from the auxiliary power unit, the APU, or sometimes from a ground air conditioning cart plugged into the aircraft. But this bleed air is far too hot and at too high a pressure to use directly in the cabin. It needs to be conditioned. This is done by the air conditioning packs.
The packs.
Usually located in the lower fuselage or tail area. These are complex units, often using an air cycle machine. Think of it like a reverse turbocharger working as a refrigerator. They use a series of heat exchangers, cooling the hot bleed air with outside ram air, a compressor to increase pressure and temperature further, and then an expansion turbine. As the air expands rapidly through the turbine, its temperature drops dramatically. This cold air is then mixed with some filtered cabin recirculation air and warmer trim air to achieve the desired cabin temperature before being distributed.
Fascinating.
It is. For cooling, particularly on the ground in hot weather or for smaller aircraft, many also use vapor cycle air conditioning systems. These work just like your home AC or car AC. They use a refrigerant like R134A, though newer, more environmentally friendly ones are coming, a compressor, a condenser to reject heat outside, a receiver dryer, and an expansion valve to evaporate the refrigerant and absorb heat from the cabin air passing over an evaporator coil.
And maintaining cabin pressure at altitude is vital for safety. It's like creating a small bubble of breathable atmosphere inside the plane. What are the key considerations for an AME here?
The pressurization system is absolutely crucial for occupant safety and comfort. Its main job is to maintain a cabin pressure altitude equivalent to around 8,000 feet or lower, regardless of the aircraft's actual cruising altitude, which might be 40,000 feet or more.
Why 8,000 feet?
That's generally considered the maximum altitude where people can remain comfortable and physiologically safe without needing supplemental oxygen for extended periods. The system ensures sufficient oxygen partial pressure for everyone on board. It also controls the rate of pressure change during climb and descent, preventing rapid changes that can cause ear discomfort or pain for passengers and crew, and it provides ventilation, circulating fresh conditioned air and removing odors and stale air.
And structural implications.
Huge structural implications. A major challenge in aircraft design has been managing the stress on the fuselage from repeated depressurization cycles on every flight. This cyclic loading can lead to metal fatigue over time. This concern was a major driver behind the FAA's aging aircraft programs, mandating increased structural inspections and modifications on older airframes, a direct and significant maintenance impact.
So how is the pressure actually controlled?
Cabin pressure controllers manage the process. Traditionally, these were complex pneumatic devices, but modern aircraft almost universally use automatic electronic controllers. These are often integrated with the Flight Management System, FMS. The FMS can provide destination airport elevation and flight plan data, allowing the controller to automatically schedule the entire pressurization profile for the flight, optimizing comfort and efficiency. The actual pressure level is controlled by modulating the outflow valve. This is usually a large valve or a set of valves located in the aft fuselage area. It controls how much air is allowed to leak out of the pressurized cabin. By precisely controlling this outflow, the system maintains the desired cabin pressure differential.
So it's constantly letting a controlled amount of air out.
Exactly. Bleed air comes in, conditioned air is distributed, and the outflow valve lets the excess out to maintain the target pressure. There are also safety valves, positive pressure relief valves to prevent overpressurization, and negative pressure relief valves to prevent the outside pressure from becoming higher than the cabin pressure, for example, during a rapid descent. Thermal switches are also incorporated, especially near bleed air ducts, to detect overheat conditions caused by pneumatic leaks or air conditioning pack malfunctions, potentially shutting off bleed air supply to prevent damage.
And for the AME, what's key for maintaining these complex environmental systems? Are there any common pitfalls or essential procedures?
Well, for vapor cycle system, servicing requires specialized tools like refrigerant manifold gauge sets and recovery recycling charging service units. Handling refrigerants requires certification in many places due to environmental regulations. You can't just vent them.
Right, environmental responsibility.
Absolutely. Purging the system, safely recovering the existing refrigerant, and then evacuating it using a deep vacuum pump are critical steps before opening the system for maintenance or component replacement. Evacuation removes air and, crucially, moisture, which can freeze or cause corrosion inside the system. Recharging is done very precisely by weight, using the exact type and amount of refrigerant and compatible oil specified in the aircraft maintenance manual. Overcharging or undercharging significantly impacts performance and can damage components.
And for the pneumatic side, the bleed air systems.
For pneumatic systems, monitoring bleed air manifold pressure and temperature via cockpit gauges fed by transmitters is essential during operation and testing. Understanding the logic of the isolation valves is crucial. These valves allow sections of the bleed air system to be shut off in case of a leak, overheat, or for certain operational configurations like engine start. This provides redundancy. You can often operate safely on one engine's bleed air if the other side has a problem, but it also means understanding complex valve logic during troubleshooting, checking for leaks, inspecting ducting for security and damage, and verifying overheat protection systems are all routine AME tasks.
Okay, let's talk about something nobody wants to think about. Fire on an aircraft. It's the ultimate nightmare scenario. What systems are in place to detect and fight it, and how does an AME ensure they're ready?
Detection systems are the first line of defense, providing early warning. There are various types used in different zones, like engines, APUs, cargo bays, and lavatories. For engines and APUs, you often find thermocouple systems, which generate a small voltage when heated, or continuous loop systems.
Continuous loop.
Yeah, these are like long, thin sensor tubes routed through the protected area. There are different types. Fan wall systems use a core material whose electrical resistance decreases rapidly with high temperature, triggering an alarm. They also have a feature where resistance increases very quickly if there's an electrical short, helping differentiate a fire from a short circuit. Kids' systems work differently, often based on detecting the rate of change of resistance or gas pressure inside the tube, again helping to distinguish a rapid-fire heat rise from a slower overheat or electrical fault. There are also pneumatic continuous loop systems that rely purely on gas pressure changes inside the tube.
And for cabins and cargo.
Smoke detectors are the primary means there. You typically find optical, light refraction or obscuration types or ionization types. They're mandatory in cargo compartments and lavatories. Flame detectors, sensing UV or IR radiation, and carbon monoxide detectors might be used in specific areas too. A typical lavatory smoke detector, for instance, might be powered by the aircraft's 28-volt DC bus. If it detects smoke, it'll trigger a local red alarm, LED, and horn inside the lavatory, activate an attendant call light outside, and also send a signal to the central monitoring systems in the cockpit. For an AME, periodic functional testing of all these detectors and their associated warning circuits is a highly critical maintenance task.
Once detected, how are fires actually fought on board? It's not like you can just call the fire department at 35,000 feet.
Indeed not. For major zones like engine nacelles, APU compartments, and cargo bays, fixed fire extinguishing systems are installed. These are designed to rapidly flood the protected area with an extinguishing agent that chemically interrupts the combustion process or displaces oxygen. The most common agent used for decades has been Halon 1301. It's extremely effective and relatively safe for occupied spaces in short bursts, though it's an ozone-depleting substance, and replacements are being phased in on newer designs.
HRD systems.
Yes, these are high rate of discharge, or HRD, systems. They use pressurized containers holding the halon, or alternative agent, and are designed to discharge the entire contents very rapidly, typically within just 1 to 2 seconds, through dedicated plumbing and nozzles into the fire zone. The goal is rapid knockdown of the fire. Activation is usually done from the cockpit. Engine and APU fire switches or handles are critical controls. Pulling the fire handle for a specific engine typically does several things automatically. Shuts off fuel flow to that engine, closes the hydraulic shutoff valve, trips the generator field, and arms the extinguishing agent discharge bottles for that engine.
So pulling the handle prepares everything.
Exactly. Then, rotating the handle or pressing a discharge switch fires one of the extinguisher bottles. Often there are 2 bottles per engine, allowing for a second shot if needed. These fire handles often have mechanical locks to prevent accidental activation, but these can be manually overridden by the flight crew if the fire detection system is suspected of malfunctioning. Cargo compartment systems are also typically activated manually by the flight crew from the cockpit if smoke is detected in a specific cargo bay.
And for smaller fires, that might occur in the cabin or flight deck.
Portable fire extinguishers are strategically located throughout the cabin and flight deck for immediate use by the crew or flight attendants. Different types are used for different kinds of fires. Halon portable extinguishers, often Halon 1211, are effective on electrical fires, Class C, and flammable liquid fires, Class B, because they are non-conductive and leave no residue. Water extinguishers, often containing water mixed with an anti-freeze agent, are used for Class A fires involving ordinary combustibles like paper, fabric, or wood.
What about CO2 or dry chemical?
Carbon dioxide, CO2, and dry chemical powder extinguishers are generally considered unsuitable for use inside aircraft cabins. CO2 displaces oxygen, which is hazardous in a confined space, and the discharge can cause cold burns or static electricity buildup. Dry chemical powders can be corrosive to electronics, impair visibility, and cause respiratory irritation. So you primarily see halon and water portables. Maintenance involves regular visual inspections, checking pressure gauges on the portable units, verifying hydrostatic test dates, and ensuring proper mounting and accessibility. For the fixed systems, it involves checking the integrity of the sensing loops, testing the warning circuits, and periodically weighing the HRD bottles to ensure they contain the correct amount of agent.
Speaking of life support, oxygen is absolutely non-negotiable at altitude. How is it managed, stored, and distributed for both crew and passengers?
Right, as altitude increases, atmospheric pressure drops, and so does the partial pressure of oxygen. Above certain altitudes, the human body can't get enough oxygen from the ambient air, leading to hypoxia. Aircraft oxygen systems compensate for this by providing supplemental oxygen, either continuously or as needed. In unpressurized aircraft, these are primary life support systems used routinely above certain altitudes, for example 10,000 or 12,000 feet. In pressurized aircraft, the built-in oxygen system serves as a critical backup in case of pressurization failure or smoke fumes in the cockpit. Portable oxygen is also carried for first aid or walk-around use by the crew.
Where does the oxygen come from?
Oxygen sources are typically gaseous oxygen stored in high-pressure cylinders. These cylinders are painted green and clearly marked aviators breathing oxygen. This specific type of oxygen is highly pure and, crucially, has a very low moisture content, typically a maximum water level of 0.02 milliliters per liter. This is extremely important to prevent water vapor from freezing in the tiny passages of regulators or valves at the very low temperatures found at high altitude, which could block oxygen flow.
That tiny detail is critical.
Absolutely critical. Liquid oxygen, or LOX is another form, stored at extremely low temperatures. It offers significant space and weight savings, but requires specialized handling and equipment, so it's primarily used in military aviation. For emergency passenger oxygen systems in airliners, chemical oxygen generators are very common. These are typically located above passenger seats. When activated, usually by pulling down on a mask that drops automatically, a chemical reaction starts inside the generator canister, often involving sodium chlorate and iron powder. This reaction produces breathable oxygen through controlled burning. They provide oxygen for a limited duration, typically 12-15 minutes, long enough for the aircraft to descend to a safe altitude.
How do AMEs handle oxygen servicing? It sounds like it could be quite hazardous if not done correctly. Pure oxygen is highly reactive.
It is extremely hazardous if not done correctly. Oxygen servicing requires strict procedures and extreme cleanliness. Pure oxygen vigorously supports combustion, and many materials, especially oils and greases, can ignite spontaneously and explosively in its presence.
So no grease monkeys allowed near the O2 cart.
Definitely not. Technicians must consult the manufacturer's manual, ensure the correct type of aviators breathing oxygen is used, and use dedicated oxygen servicing carts. These carts typically have multiple supply cylinders connected to a manifold with regulators and filters. Safety precautions are paramount. Work in a well-ventilated area, no smoking or open flames nearby. Ensure hands and tools are completely free of oil or grease. Valves must be opened slowly to avoid heat buildup from rapid compression, adiabatic compression. The fill hose must be purged with oxygen to remove any air or moisture before connecting it to the aircraft system. Pressure must be monitored frequently during the filling process.
How is the oxygen distributed?
Oxygen flows from the high-pressure storage cylinders through pressure regulators that reduce the pressure to a usable level for the masks. Distribution systems are either continuous flow, which provide a constant flow of oxygen mixed with cabin air, common for passenger masks, or demand flow, where oxygen is delivered only when the user inhales, conserving the supply, typical for flight crew masks. Diluter demand regulators can provide a mix of air and oxygen, or 100% oxygen, depending on altitude and settings. Pressure demand regulators provide oxygen under positive pressure, forcing it into the lungs, necessary at very high altitudes.
And indications.
Pilots have indications of oxygen cylinder pressure, warnings for low pressure, and often individual flow indicators, like a blinker in the mask hose, to confirm oxygen is flowing. There's also usually a green blowout disc on the fuselage exterior. If the oxygen cylinder overpressurizes, for example, due to overheating, this disc will rupture, safely venting the oxygen overboard. Seeing this disc missing indicates an overpressure event occurred and the system needs inspection.
And leak checks.
Leak testing must only be done using an oxygen-safe leak check fluid, typically a special soap solution approved for oxygen use. Using standard leak check fluids containing incompatible chemicals could cause a fire or explosion when exposed to pure oxygen. Cleanliness and using the right materials are absolutely critical when working with oxygen systems.
Mobility, protection, and integrated systems.
Okay, if electricity is the lifeblood and nerves, hydraulics are definitely the muscles of the aircraft. They power some of the heaviest and most critical moving parts.
Absolutely. Hydraulic systems are all about transforming fluid pressure into significant mechanical force. They are the workhorses for operating things like landing gear retraction and extension, deploying large flaps and slats, moving primary flight control surfaces on bigger aircraft, operating spoilers, and powering the brakes. System complexity varies hugely. A small aircraft might just have a simple, independent system for brakes, but a large transport aircraft will have multiple, complex, redundant hydraulic subsystems, typically 3 independent systems.
3 systems for redundancy.
Exactly. Each system will typically have its own reservoir to hold fluid, multiple pumps, engine-driven and electric motor-driven, accumulators to store pressure and dampen surges, filters to keep the fluid clean, and numerous valves and actuators, all operating at high pressures, typically 3,000 psi, but sometimes up to 5,000 psi on newer designs like the A380 or F-35.
What are the main types of systems?
Broadly, 2 main types. Open center systems are simpler, often found on lighter aircraft. In these, fluid flows continuously from the pump through the selector valves and back to the reservoir with little pressure until a selector valve is actuated. Actuating a valve blocks the return path, causing pressure to build up and operate the component. Closed center systems are much more common in larger aircraft. In these, the fluid is maintained under constant pressure whenever the system is operating. This is usually achieved either by using a variable displacement pump, which automatically adjusts its output flow based on system demand to maintain pressure, or by using a constant delivery pump combined with a pressure regulator or unloader valve that diverts excess flow back to the reservoir when system pressure is reached.
Are all hydraulic fluids compatible? I imagine mixing them could be a really catastrophic error for an AME.
Crucially, NO. They are absolutely not compatible, and mixing them is a major hazard. This is one of the most important things for an AME to know and respect. Technicians must use only the correct category of replacement fluid specified for that aircraft. There are generally three main types: mineral-based, like MIL H5606, usually dyed red; phosphate ester-based, like Skydrol or Hijet, usually purple; and synthetic hydrocarbons, like MIL H83282 red, developed as a fire-resistant alternative to 5606.
What happens if you mix them?
Bad things. For example, contaminating fire-resistant phosphate ester fluid, Skydrol, with even a small amount of mineral-based fluid, 5606, can destroy its fire resistance properties, damage seals designed for Skydrol, and create a gummy residue that clogs filters and valves. It usually requires a complete system flush and seal replacement, incredibly expensive.
And Skydrol needs careful handling.
Yes, phosphate ester fluids like Skydrol require careful handling. They are excellent hydraulic fluids, very fire-resistant, but they are potent solvents. They can irritate skin upon prolonged contact, damage many paints and plastics, and require specialized seals, like butyl rubber or Teflon, throughout the system. Spills need to be cleaned up immediately using approved methods.
You mentioned redundancy multiple systems. How are they powered?
Modern aircraft, like the Airbus A380 or Boeing 777, have incredible redundancy. The 777, for example, has three independent 3,000 psi hydraulic systems: left, center, right. Each system is typically powered by multiple sources for resilience. For instance, the left and right systems might each have an engine-driven pump, EDP, on their respective engine, plus an AC electric motor-driven pump, ACMP, as a backup or for ground operations. The center system might have two ACMPs, plus maybe pressure supplied from the RAT in emergencies. This ensures that even with multiple failures, like losing an engine and an electric pump, sufficient hydraulic power remains available for critical flight controls.
And safety devices within the system.
Lots of safety devices. Pressure relief valves are essential to protect the system from overpressurization if a pump or regulator fails. Hydraulic fuses are sometimes installed. These detect a sudden, abnormally high flow rate, indicating a major leak, like a burst line, and automatically shut off fluid flow to that leaking branch, preserving fluid and pressure for the rest of the system.
Clever.
Actuators, of course, are the components that convert fluid pressure into the linear or rotary motion needed to move landing gear, flaps, control surfaces, etc. And filters are absolutely critical throughout the system to remove contaminants from the fluid. Cleanliness is paramount for hydraulic system reliability. Even tiny particles can jam valves or damage pumps.
What do pilots and maintenance crews actually see regarding hydraulic status? How do they monitor these powerful systems?
On the flight deck, the primary indications are typically system pressure and fluid quantity, reservoir level, for each independent hydraulic system. These are often displayed on dedicated gauges or, more commonly now, on the AKIs or ECAM electronic display screens. Fluid temperature might also be displayed, as overheating can indicate a problem like a failing pump.
And brake pressure?
Yes, brake pressure usually has a separate indicator, showing the pressure being applied to the brakes, often sourced from one or more of the main hydraulic systems via the brake control valves. For maintenance crews on the ground, there are often direct reading fluid quantity indicators on the reservoirs themselves, or electronic indicators accessible via a maintenance panel. Low fluid quantity switches in the reservoir will trigger cockpit alerts. Overheat sensors, often located in the pump case drain lines or near electric motors, provide warnings of potential pump failures. It's worth noting that electric motor-driven pumps, ACMPs, are generally more susceptible to overheating than engine-driven pumps, so monitoring their temperature is often integrated into the system logic.
Okay, let's talk about the landing gear. It endures immense forces during takeoff and especially landing. What are the key elements for an AME to focus on during inspection and maintenance?
The landing gear is a marvel of engineering, designed to absorb and dissipate the enormous energy of landing. The most common configuration is the tricycle-type gear. Two main gear units under the wings or fuselage, and a nose gear unit. Key components include the shock struts, also called oleo struts or just oleos. These are the big telescopic legs that absorb the landing shock and support the aircraft's weight on the ground. They work using a combination of compressed nitrogen or air, acting as a spring, and hydraulic fluid flowing through orifices, controlled by metering pins or tubes, to provide damping during compression and extension. Proper inflation pressure, nitrogen, and fluid level are critical for their function.
So they're both a spring and a shock absorber.
Exactly. You also have complex support structures, beams, links, drag braces, side braces that transmit the landing loads into the aircraft structure. Gear alignment units ensure the wheels track straight. Retraction and extension systems are typically hydraulically operated, controlled by a selector lever in the cockpit. This involves a complex sequence of operations. Hydraulic pressure, directed to door actuators to open the gear doors, then to retraction actuators to raise the gear, then up blocks engaged to hold the gear up, and finally the doors close. Extension is the reverse sequence, with down locks engaging to secure the gear in the extended position. Check valves and sequence valves ensure everything happens in the correct order.
And indications.
Pilots get clear indications, usually lights, typically green for down and locked, red for in transit or unsafe, and off or up and locked for each gear unit. On the 737, for example, having red lights illuminated above the green lights indicates the gear is in transit. These indication systems rely on position sensors and switches on the gear and locks.
Safety devices are obviously paramount here, given the critical function.
Absolutely paramount. Ground locks are physical devices, pins or sleeves, often with red flags, installed by ground crew to mechanically prevent the gear from retracting inadvertently while the aircraft is on the ground, especially during maintenance when hydraulic power might be applied.
Essential safety step.
Essential. Nose wheel centering devices, often cams or internal mechanisms in the nose gear steering, automatically align the nose wheel straight ahead before retraction, ensuring it fits correctly into the wheel well without damaging the structure. Proximity switches or load sensors, commonly called weight on wheels or WLW switches, sometimes implemented as logic cards, are critical. They detect whether the aircraft's weight is on the wheels or not. This air-ground status information is fed to numerous other aircraft systems.
What kind of systems?
Things like preventing landing gear retraction handle movement on the ground, enabling thrust reversers only on the ground, disabling stall protection systems on the ground, enabling ground spoilers, controlling pressurization, outflow valve position, etc. Some advanced load sensors can even provide an estimate of the aircraft's weight while it's on the ground. Position indicators in the cockpit, as mentioned, show the status of each gear.
You mentioned a critical caution for maintenance.
Yes, extremely important. Always, always deflate high-pressure tires before attempting to remove the wheel assembly from the axle, especially if there's any suspicion of damage to the wheel tie bolts.
Why is that so critical?
Aircraft tires are inflated to very high pressures, often over 200 psi. If the tie bolts holding the wheel halves together are damaged or fail during removal, the stored energy in that compressed air can cause the wheel halves to separate explosively, potentially causing fatal injuries from flying debris. Deflating the tire removes that stored energy hazard.
Wow. Good to know. What about the wheels and bearings?
Wheels themselves are typically made of aluminum or magnesium alloy, often two-piece designs bolted together. They need to be statically balanced. Regular inspection for cracks, corrosion, and heat damage, especially near the brakes, is vital. Bearings, usually tapered roller bearings, support the wheel on the axle. They require careful cleaning using approved solvents like Varsol or Stoddard solvent, never gasoline, thorough inspection for any pitting or discoloration, and proper lubrication with approved aircraft wheel bearing grease. A crucial point: never spin a clean, dry bearing with compressed air. The high speed without lubrication can instantly score or damage the precision metal surfaces.
Brakes are obviously vital for stopping. How do aircraft brakes work, especially on large jets, and what are the complexities for an AME?
Aircraft brakes have to dissipate incredible amounts of kinetic energy as heat. Single-disc brakes, similar to cars but heavier duty, are common on lighter aircraft. Heavy aircraft almost universally use multi-disc brakes, often carbon composite discs now, instead of older steel discs. Carbon brakes are lighter, perform better at high temperatures, and last longer, though they are more expensive initially.
Segmented rotors.
Yes, multi-disc brakes often use segmented rotors, multiple rotating discs, rotors, keyed to the wheel, interleaved with stationary discs, stators, keyed to the axle brake housing. Hydraulic pressure forces a piston or multiple pistons to clamp this stack together, creating immense friction. Multi-disc brakes often have numerous hydraulic cylinders actuating them, sometimes supplied by two different aircraft hydraulic systems for redundancy. If one system fails, you still have braking capability.
And how is braking controlled?
Power brake systems use metering valves. These valves receive hydraulic pressure from the main system and modulate it to the brake units in proportion to how hard the pilot pushes on the rudder pedals, toe brakes. They often incorporate mechanisms to provide artificial feel back to the pilot's feet using springs and pistons so they can judge the braking effort. Many systems also include an auto brake function. The pilots can select a desired deceleration rate, for example, low W, MERD, max, and the system will automatically apply and modulate brake pressure after touchdown to achieve that rate, freeing up the pilots to focus on steering and thrust reversers. Auto brakes are also often used after takeoff to stop wheel rotation before retraction.
Emergency braking.
Yes, there's always an emergency brake system. This typically uses an independent hydraulic source, like an accumulator charged by one of the main systems, or sometimes a separate system, or sometimes separate brake assemblies, ensuring some braking capability even if all main hydraulic systems are lost.
And anti-skid, like ABS for planes.
It's exactly like ABS, but arguably even more critical given the speeds and weights involved. Anti-skid systems are crucial for maintaining directional control and achieving maximum braking effectiveness without blowing tires. They use wheel speed sensors, usually small generators or proximity sensors, on each braked wheel to monitor its rotational speed. If a sensor detects that a wheel is decelerating too rapidly, indicating an impending skid or lockup, the anti-skid control unit signals a control valve to momentarily release brake pressure to that specific wheel, allowing it to spin up again. This cycle happens rapidly, keeping the wheel just at the point of maximum braking friction without skidding.
Smart system.
Very smart. They also include locked wheel protection. If a wheel completely stops rotating while others are still turning, for example, due to hydroplaning on one side, the system releases brake pressure on the locked wheel to allow it to spin up again. Anti-skid systems are often automatically inhibited during takeoff rotation and immediately after touchdown for a brief period to ensure brakes are available if needed for retraction braking or initial stopping effort before the anti-skid logic fully takes over. Maintenance involves checking sensors, wiring, control units, and control valves for proper operation and freedom from leaks.
And finally, the direct connection to the ground itself, tires. What makes aircraft tires so unique and demanding compared to, say, car tires?
Aircraft tires are highly specialized pieces of equipment. Unlike car tires designed for long life and continuous operation, aircraft tires are built primarily for extremely high impact loads during landing and very high ground speeds, but only for relatively short durations, takeoff roll, landing roll, taxiing.
So, short bursts of extreme stress.
Precisely. They are designed to deflect significantly more than car tires under load to help absorb landing shocks. They are classified by their size, speed rating, and ply rating. The ply rating indicates the relative strength of the tire carcass, the reinforcing layers of fabric, usually nylon or aramid, encased in rubber. It doesn't necessarily mean the actual number of plies anymore, but is an index of load-carrying capacity.
Tube type or tubeless?
Most modern aircraft use tubeless tires, which have an integral inner liner bonded to the inside of the carcass to hold the air pressure, similar to modern car tires. Some older or smaller aircraft might still use tube-type tires. Critically, only tires specified by the aircraft manufacturer in the maintenance manual or parts catalog should ever be installed. Using an incorrect size, ply rating, or speed rating could lead to tire failure, potentially with catastrophic consequences during takeoff or landing. For an AME, proper inflation pressures, checked regularly when tires are cool, thorough visual inspection for cuts, cracks, bulges, flat spots, chevron cutting, or wear, down to the tread wear indicators, and knowing when to replace them based on manufacturer limits are absolutely fundamental maintenance practices.
Okay, let's talk about battling the elements. Ice is a major hazard for flight safety, capable of completely disrupting airflow and adding dangerous weight. How do aircraft combat this threat?
Ice is a huge hazard. It's insidious. Ice accretion, or buildup, on critical surfaces like wings, stabilizers, propellers, engine inlets, and flight instrument probes can have severe consequences. It increases aerodynamic drag significantly. It reduces lift, potentially leading to a stall at a much higher airspeed than normal. It adds weight. It can cause severe vibration if it builds up unevenly, especially on propellers or engine fan blades. It can impact instrument readings by blocking pitot tubes or static ports, leading to erroneous airspeed or altitude information.
In chunks breaking off.
Yes, Large chunks of ice shedding from wings or propellers can cause engine flameout due to foreign object damage, FOD, or cause structural damage if they impact the fuselage or tail surfaces, especially on aircraft with rear-mounted engines. Ice detectors, various types exist, sensing temperature, moisture, or physical accretion, alert the flight crew to icing conditions. On some aircraft, these detectors can automatically activate the ice protection systems.
Anti-icing versus de-icing, what's the difference?
A fundamental distinction. Anti-icing systems are designed to be turned on before or upon entering icing conditions to prevent ice from forming in the first place. De-icing systems are designed to remove ice after it has already formed. Understanding which system is which and how it operates is crucial for both pilots and AMEs.
How are these systems typically implemented, and what are the specific maintenance considerations for each type?
One common method, especially for wing and engine inlet anti-icing on jets, is thermal pneumatic anti-icing. This uses hot bleed air taken from the engine compressors or the APU. This hot air is ducted through pipes inside the leading edges of the wings, horizontal stabilizers, vertical fin, and engine nacelle inlets. It heats the skin surface above freezing, preventing ice from adhering. Control valves regulate the flow and temperature of this bleed air. Control might be managed by a dedicated computer, like the ACIPS airfoil and catalyzed protection system card mentioned in some manuals, ensuring symmetrical heating on both wings to maintain aerodynamic stability. Maintenance involves checking ducts for leaks, security, insulation integrity, and verifying control valve operation.
And electrical heating.
Thermal-electric anti-icing is also widely used, especially for smaller components or areas where routing hot air is difficult. It uses electrical heating elements embedded in or bonded to the surface. This is common for flight instrument probes, PO tubes, static ports, angle of attack sensors. These get extremely hot very quickly, so caution is needed when working near them on the ground after power has been applied that can cause nasty burns.
Good warning.
Windshields are also often electrically heated, either using fine wires embedded within the glass plastic layers or transparent conductive films deposited on the surface. Propellers on turboprop aircraft often use electrothermal boots bonded to the leading edges of the blades, with power transferred through slip rings and brushes at the propeller hub. Maintenance involves checking electrical continuity, resistance values of heating elements, bonding integrity, and proper operation of control circuits and timers.
And ground de-icing, that's different again.
Yes, ground Deicing anti-icing is performed on the ground before flight when conditions warrant. It involves spraying the aircraft surfaces with special heated fluids, typically mixtures of glycol and water. Type I fluids, usually orange-pink, are primarily for de-icing, removing existing ice now, and offer limited anti-icing protection, short holdover time. Type 2, light yellow, and Type 4, green fluids are thicker, containing polymers, used for both de-icing and anti-icing, providing longer holdover times by forming a protective film that prevents snow or ice from adhering before takeoff. Applying these fluids requires specialized equipment and procedures, following strict manufacturer guidelines, including avoiding spraying into engines, probes, or control surface gaps. Holdover times are critical and depend on fluid type, concentration, and prevailing weather conditions.
And what about de-icing boots, a more classic approach sometimes seen on older or smaller aircraft? How do they work?
Right. Pneumatic de-icing boots. These are inflatable rubber elements bonded to the leading edges of wings and tail surfaces. They're typically powered by engine-driven air pumps, sometimes wet-type pumps lubricated with oil, requiring an oil separator downstream, or sometimes by regulated bleed air. The system rapidly inflates the boots with air pressure, causing them to swell and crack off any accumulated ice. Then vacuum is applied to deflate the boots rapidly and hold them tightly against the airfoil shape to minimize aerodynamic drag when not inflated.
So they inflate and deflate in sequence.
Usually, yes. A sequence timer controls solenoid valves to inflate and deflate different sections of the boots. For example, outboard wings, then inboard wings, then tail, in a cycle to shed ice effectively. Control valves direct the pressure and vacuum, and deflate valves help pull the boots down quickly. Maintenance involves regularly inspecting the boots for cuts, tears, punctures, and proper adhesion. Special conductive cement is often used for repairs to help dissipate static electricity buildup. Troubleshooting might involve checking for leaks in the boots or plumbing, verifying pump output, pressure vacuum, and ensuring the timer and control valves are sequencing correctly. Issues like slow inflation or boots not deflating properly can significantly impact their effectiveness and even aerodynamics.
And finally, for rain, which can severely impact visibility, especially during approach and landing. What systems handle that?
Rain control systems are essential for maintaining forward visibility. The most common method is windshield wipers, much like on a car, but usually much larger and more powerful. They can be electrically or hydraulically powered, often with separate systems for the left and right windshields for redundancy. Pilots can typically control the speed, low intermittent.
Any other methods?
Yes, some aircraft use chemical rain repellents. A special fluid is sprayed onto the windshield, causing water to bead up and blow away easily in the airflow. Pneumatic jet blast systems have also been used, blowing high-velocity air, often bleed air, across the windshield to clear rain. And increasingly, advanced hydrophobic coatings are applied to windshield surfaces during manufacturing or maintenance. These coatings make the surface repel water very effectively, often reducing or eliminating the need for wipers or repellents. For an AME, maintenance involves inspecting and replacing wiper blades, checking repellent fluid levels and system operation, or ensuring the integrity and proper application of hydrophobic coatings.
Okay, let's quickly touch on some of the supporting cast of systems, the ones that often go unnoticed but are vital for operations, passenger experience, and meeting regulations, equipment and furnishings, for instance.
Yeah, this area, EASA Module 6, covers a surprising amount that's relevant for AMEs, integrating safety regulations with passenger comfort and logistical support. EASA certification specifications, particularly CS25 for large commercial transport aircraft, dictate many requirements here. Things like the minimum number and location of portable fire extinguishers, standards for seat belts and harnesses, flammability requirements for cabin materials, emergency lighting systems, and even pragmatic limitations on cabin layout to ensure emergency exit paths are always clear and unobstructed.
And equipment layout.
Equipment layout, especially on the flight deck, is carefully considered for ergonomics and accessibility. While regulations might vaguely specify things be within arm's reach, practicalities and standardization often lead to fairly consistent locations for controls and displays across aircraft types. AMEs need to be familiar with these typical layouts for inspections and troubleshooting, ensuring everything is correctly installed and labeled.
And cargo is definitely more than just stuffing bags in a hold, right? There's a whole system for managing it safely and efficiently.
Absolutely correct. Cargo compartments on large aircraft, usually located below the passenger cabin floor, are highly engineered spaces. They're lined with fire-resistant panels and have specific fire detection and suppression systems. They're also generally much colder than the main cabin. For handling large cargo containers or pallets known as unit load devices or ULDs, many aircraft have sophisticated powered cargo loading systems. These use power drive units, PDUs, which are electric rollers or wheels embedded in the floor, often with torque control to prevent damage, to move the heavy ULDs into position.
So the loaders don't have to push them all the way in.
Right. It makes loading much faster and requires less manual effort. The floor also has numerous guides, restraints, latches, and locks to securely hold the ULDs in place, preventing them from shifting during flight. Proper loading and securing are critical for maintaining the aircraft's weight and balance. Many airliners also feature electrically or hydraulically deployed air stairs, extending from below the fuselage near a passenger door, allowing the aircraft to operate self-sufficiently at airports without requiring ground stairs or jetways. For an AME, maintenance of these systems involves regular lubrication, electrical checks on PVUs and air stairs, ensuring locks and restraints function correctly, and keeping the cargo compartments clean and free of foreign object debris, FOD.
What about pneumatic and vacuum systems? You mentioned bleed air for environmental controls, but are there other uses?
Well, dedicated vacuum systems are less common now, largely replaced by electronic gyros in modern aircraft. But older transport aircraft might still use engine-driven vacuum pumps to power gyroscopic flight instruments. Pneumatic systems using bleed air, however, remain absolutely critical in modern jets. As we discussed, bleed air is the primary source for air conditioning packs and cabin pressurization. It's also the main power source for thermal anti-icing systems on wing leading edges and engine inlets. What's important to grasp now is how highly integrated these pneumatic systems are with other aircraft systems. Control valves for bleed air supply, anti-ice, and pressurization are often managed by computers that receive inputs from various sources. Flight control computers, AFDS, the Central Information Management System, like Boeing's AMES, electronic engine controls, EEC, electrical load management, ELMS, all communicating via digital data buses.
So it's not just simple on-off valves anymore.
Not at all. Pneumatic component control is often automatic and highly responsive to various flight phases, system status conditions, and fault detection logic. For the AME, while monitoring pneumatic manifold pressure via cockpit gauges, fed by pressure transmitters, and checking for overheat indications remain important, troubleshooting often involves understanding the control logic and diagnosing inputs-outputs on the data buses, in addition to checking the physical components. Isolation valves are still key, allowing segments of the system, like bleed air from one engine, to be shut off in case of a leak or failure, relying on the system's inherent redundancy for continued safe operation.
And water and waste systems. Seems mundane, but essential for long flights.
Mundane, perhaps, but essential for passenger service and hygiene? Absolutely. Potable water, drinking water, is stored in dedicated tanks and distributed via pumps and plumbing throughout the cabin to galleys for food and beverage preparation and lavatories for sinks. Systems include filling draining provisions, filtration, sometimes heating elements to prevent freezing, and level indicators. Toilet systems have evolved significantly. Older systems might have used recirculating fluid, blue water, with electric motor-driven flushes. Modern aircraft almost universally use vacuum flush systems.
How do those work?
They use suction to remove waste, which is much more efficient and hygienic, and uses far less water per flush. The suction is generated either by an electric vacuum blower, typically used when the aircraft is on the ground, or below a certain altitude, maybe 16,000 feet, or at higher altitudes, simply by the pressure differential between the higher pressure cabin and the lower pressure outside atmosphere.
Using the altitude advantage.
Exactly. When flushed, a valve opens, and the vacuum pulls the waste through plumbing to large remote holding tanks, usually located in the aft lower fuselage. A small amount of potable water, maybe just for a second or two, is often injected to rinse the bowl during the flush. For an AME, maintenance involves ensuring the potable water system is clean, periodic disinfection is required, and leak-free, and that the vacuum waste system is functioning correctly, checking pumps, valves, seals, and ensuring tanks are properly serviced on the ground.
Okay, this brings us to the real cutting edge, the digital frontier, integrated modular avionics and information systems. This is where the magic of modern aviation truly happens.
Absolutely. The evolution of avionics architecture has been dramatic. We've moved from the older approach of having numerous discrete, standalone black boxes, each performing a specific function, with its own power supply, dedicated wiring, and often custom interface.
The federated architecture.
Right, the federated architecture. We moved towards highly integrated modular avionics, or IMA. The key concept here is shared resources. Concepts like the Common Core System, CCS, mean that shared computer processors or modules, housed in standardized cabinets, handle multiple functions that used to require separate boxes. A single powerful module might perform calculations for flight controls, manage fuel systems, process navigation data, and activate stall warnings.
So fewer boxes, shared brains.
Exactly. This significantly reduces weight, power consumption, cooling requirements, and wiring complexity. It also streamlines pilot workload by integrating many different indicators and controls into single multifunction displays, like the navigation display in D or the primary flight display, PFD. Boeing's Airplane Information Management System, AMES, on the 777 and later models, is a prime example of this IMA philosophy. AMES typically consists of two cabinets housing numerous standardized line-replaceable modules, or LRMs. These LRMs plug into a common backplane bus inside the cabinet. Different LRMs are assigned specific functions, processing information for the primary display system, PDS, flight management computation, central maintenance computing, engine data interface, flight data recording, communications management, etc. But they share power supplies, cooling, and communication pathways. These modules communicate with each other and with other aircraft systems via high-speed digital data buses. We've moved from older, slower buses like ARIN-C 429 unidirectional point-to-point and ARIN-C 629 bidirectional multi-transmitter used heavily on the 777 to newer, much faster, switched Ethernet-based networks like AFDX, Avionics Full Duplex, switched Ethernet, used on the A380, A350, 787. AFDX uses fewer wires, provides guaranteed bandwidth and latency, and uses a star topology, making it very robust and scalable. The cockpit display units we talked about, PFD, ND, IC, MFD, are driven by these powerful IMA systems, with sophisticated built-in reversionary modes to ensure critical flight information is always available, even if multiple modules or display units fail. For the AME, IMA means troubleshooting often involves interrogating the central maintenance computer, interpreting fault codes related to specific LRMs or software functions, and potentially replacing modules rather than entire black boxes. Software configuration control becomes critically important.
So it's not just the flight deck that's integrated like this. The entire cabin environment is becoming increasingly digital and networked too.
Very much so. Systems like the Cabin Services System, CSS, on the Boeing 777 are multi-feature digital systems that integrate many cabin functions. This includes the Cabin Intercommunication Data System, CIDS, for flight attendant communication, PA, call lights, etc., but also interfaces with cabin lighting control, environmental controls, water waste monitoring, and cabin network services. It uses various data buses, including connections back to the main avionics system, like AMES via RANC 629, and dedicated cabin buses like Ariane 628 for in-flight entertainment IFE systems. The Cabin Systems Management Unit, CSMU, often acts as the central processor for many of these functions.
And IFE itself is a complex system.
Hugely complex. Modern IFE systems, providing individual video screens, audio channels, games, moving maps, and sometimes internet access at each passenger seat, involve a central server computer, a distribution network throughout the cabin, often fiber optic or Ethernet, and individual seat electronic boxes, SEVs, and display uses. Troubleshooting can involve anything from software glitches to network connectivity issues to hardware failures at individual seats. Satellite communication, SACOM systems like Iridium or Inmarsat are also integrated. Iridium, for example, uses a constellation of 66 low Earth orbit LEO satellites, providing truly global voice and data coverage. The system ensures continuous connectivity through automatic handovers from one satellite to the next as the aircraft flies. These provide data links for ACARS, airline operational communications, sometimes passenger connectivity, and crucial safety communications. And external cameras, becoming more common on modern airliners, provide real-time views, like tail cam, landing gear cam, displayed on passenger IFE screens, or sometimes used by the flight crew for situational awareness, or even assisting with cargo sling operations on helicopters. All these systems are increasingly interconnected via digital networks.
And for maintenance, this massive digital shift means a completely new way of accessing and managing information, moving far beyond stacks of paper manuals.
Absolutely. Information systems have dramatically evolved. Paper manuals, while still sometimes legally required as a backup, have largely been replaced by electronic formats accessible via laptops or tablets. The electronic flight bag, EFB, in the flight deck is a prime example. EFBs are typically tablets or dedicated displays that integrate numerous databases and applications previously carried in paper form, navigation charts, approach plates, aircraft operating manuals, performance calculation software, checklists, airport maps. These databases are often updated wirelessly when the aircraft is on the ground via a Terminal Wireless LAN Unit, TWLU, connecting to the airline's network.
Huge efficiency gain.
Massive. For maintenance, technical publications are now typically delivered as digital maintenance information systems. These leverage hyperlinks for incredibly fast navigation through vast amounts of information organized according to the standardized ATA 100 chapter system. You can jump directly from a fault code to a troubleshooting procedure to a wiring diagram to a parts list, all electronically. Network server systems, NSS, onboard the aircraft act as central repositories for this digital information, managing databases and software loads. Air Traffic Information Management Systems, ATIMS, might handle communication links for ATC data like digital ATIS or clearances. These onboard networks often employ firewalls to securely separate the critical avionics and domain from the open world domain used for passenger internet access or non-essential cabin systems, preventing unauthorized access or interference. This digital transformation makes troubleshooting faster, more accurate, provides immediate access to the latest information, reduces human error in referencing data, and ultimately helps reduce aircraft turnaround times, all vital benefits for AAS in today's fast-paced environment. Outro.
Wow. Okay. We've just completed a truly comprehensive deep dive into, well, the foundational and the really cutting-edge systems that make modern aviation possible.
It's quite a journey through the aircraft, isn't it?
It really is. From the fundamental forces of flight and the very structure holding it all together to that intricate web of electrical power, hydraulics, environmental controls, and then the advanced digital brains, the IMA and information systems that manage it all. What an incredible look beneath the skin.
It really highlights, I think, that aircraft maintenance engineering is an incredibly dynamic and absolutely critical field. You, as the AME listening to this, you're not just working on individual components in isolation. You're ensuring the harmonious operation of these complex, deeply interconnected systems. Your understanding of everything from, a simple Borden tube measuring pressure to a multi-redundant fly-by-wire computer processing millions of calculations per second. That's what keeps these complex machines safe and operational worldwide. The meticulous standards, the layers upon layers of redundancy we talked about, the constant drive for efficiency, They all ultimately rely on your knowledge and your skill.
And here's where it gets really interesting for the future, I think. As aircraft continue to evolve with ever-increasing reliance on integrated modular avionics, software-defined functions, and digital information systems, that traditional black box of mechanical parts is becoming more and more a digital black box.
That's a good way to put it.
It raises a really important question, doesn't it? How will the art, and it is an art, of hands-on troubleshooting adapt and evolve when so much of an aircraft's health and performance is managed and monitored by essentially invisible streams of data flowing through networks?
It's a significant shift.
Your role, fundamentally, remains the same, ensuring safety and reliability. But the tools you use, the techniques you employ, maybe even the way you think about problems will continue to transform. Definitely something to mull over as you work with these incredible machines, and something that will likely redefine your role in the coming years.
Exactly. And that knowledge we've discussed, it's most valuable when it's deeply understood and actively applied. There's always more to learn in this field. Keep asking those questions. Keep digging into the why behind the systems. That critical thinking, that curiosity is absolutely essential in a world of ever-increasing complexity and information, where the solutions of tomorrow might be found hidden in the data logs of today.
Couldn't agree more. That's it for this deep dive. We hope you feel thoroughly refreshed, maybe a bit better informed about the incredible world beneath the skin of an aircraft. Until next time, keep learning, keep exploring, and keep those insights coming.